Since we didn't have a chance to introduce Chapter 7 today because of the power outage, this is going to be the lecture presentation for Chapter 7. And let's see, position some things here. And now, so all of Chapter 7 has to do with introducing common elementary steps that we will encounter in chemical reactions. Remember from general chemistry, chemical reactions rarely occur. In fact, I can't think of a single example, except for maybe acid dissociation, perhaps. Examples of reactions that occur in a single step. Most of them occur in 2 or more elementary steps. And remember, an elementary step is, say we have a reaction here. What we're talking about is simple steps that occur in here between the overalls. And I won't go into a lot of detail there because you should have gotten that in general chemistry. But another characteristic of elementary steps is they have one transition state. In other words, if we have the progress of the reaction here, and we have the energy of the reactants and products here, an elementary step will have reactants somewhere, and then we'll go to an activated complex when we've added some energy here. That's the activation energy. And that complex will then, with that much energy, end up with products. So these are the products, these are the reactants. And this is the activated complex. Or sometimes it's called the transition state. Okay. So think back also to chemical kinetics. In chemical kinetics, we introduced the concept of, this is in general chemistry, we introduced the concept of elementary steps. And the primary purpose for doing that in kinetics was that these several steps of a chemical reaction, these elementary steps, you might have step 1, 2, and 3, and then you go from reactants to products and go from and then you may have A plus R equals B, and then B plus another B would equal C, and then C plus R, excuse me, no, A plus B equals R, and then 2 other B's would make a C, and then C plus R would make a D. And these intermediate products, you don't even know they're there. But we introduced this concept in kinetics because each one of these steps occurs at a different rate. And the slowest rate, say, let's just arbitrarily say, this one's the slowest. Of all 3 of those, that one's the slowest. This one is the one that determines the rate of the reaction, right? The slowest one, that's the bottleneck. Okay, carry that over into organic chemistry. And now we're looking at elementary steps as a way of understanding overall reactions that we have largely haven't gotten to yet. We're looking at elementary steps first. trying to get a handle on the most common types of elementary steps. Now, there are several that are very common, but there are quite a few that we're going to cover in this chapter. So we've already looked at one of them, right? And I'm going to try to list them over here as we get to them. One that we've done already is the proton transfer. Okay, so proton transfer is one. Let's see. That's one. And as we proceed through the chapter, we're going to get more. In fact, we should see a total of 9 elementary steps that we're going to look at here. Yes, proton transfer was an elementary step. It occurs as a single event, and that's always the case. An elementary step occurs with a single event. Actually, we're going to get 10. We're going to have 10 elementary steps that are possible. So this is number 1. I hope I have enough room. I'll try to put everything up here on the board so we can list them as we come to them. All right, so let's proceed to the next one. This is our proton transfer step. And this is fairly easy to understand because we've already been introduced to acid-base reactions in general chemistry. But we're expanding here on this concept of proton transfer in terms of other types of acids and bases. We don't normally think of methane or methanol as an acid or a base, but they do behave like that under certain circumstances. But the concept that permeates, that follows a thread through all of these elementary steps, is that you have an electron-rich site. It may be on the same molecule, but you have an electron-rich site and an electron-poor site. And the electron-rich site is said to attack the electron-poor site. And that's what initiates the reaction. And that's what the curved arrows are for also. Curved arrows, remember, proceed from lone pairs or from bonds, and they attack atoms. Okay, so here's our example from proton transfer. We know that opposite charges attract, and that atoms in the first and second row of the periodic table, first row would be hydrogen and helium. They obey, well, helium, you can forget about helium. Hydrogen obeys the duet rule. Right? It can only have 2 electrons. But in the second period, those atoms all obey the octet rule. They will, they tend toward 8 electrons in their neighborhood. Now, sometimes they're deficient. Rarely are they excessive, but sometimes they are deficient, such as with a cation, a carbocation. Say we have like this, that, bound to something, and that gives us a positive charge. This is an octet deficient carbon. We'll see that again later. All right. So in this case, we want to identify the electron poor hydrogen atom in methanol, and then use that information to draw the mechanism for methanol reacting with the amine anion using a proton transfer. So we look at what we've got, right? Both the methanol and the H2N minus. What kind of charge characterizes electron poor atoms, and which hydrogen in methanol bears that kind of charge? Because why did we say that it's going to be electron poor hydrogen? Well, because HN, this species right here, right, has a minus charge. It has 2 lone pairs. Right? It's electron rich by comparison to methanol. All right, so we're saying that an electron poor atom tends to have a partial or full positive charge. And because the oxygen atom in methanol is electronegative, very electronegative, then it tends to draw electron density away from hydrogen that is attached to it. That gives the hydrogen a slight positive. Well, I'm going to show you in the next slide a slight positive charge. A formal, actually, it's only a slight positive charge. We would say this. OH. Like that, I think. Oh, I'm sorry. I put too many carbons in there. Here we go. There, methanol. So this draws electron density. And remember, in general chemistry, we talked about polar bonds. This is a polar bond, right? Like that. That means this is slightly positive and this is negative. Okay? So there's your positive hydrogen. And here's your lone pairs. So these are going to be what we call nucleophiles because they have excess electrons. They're looking for positive charge. They're looking for a nucleus. And that's the term that we're using there. Nucleophile is anything that's looking for positive charge or deficiency in electrons. So this is the nucleophile. Right? It loves the nucleus. Nucleus is always positively charged, so it loves the nucleus. This one is the electrophile. Right? It's looking for electrons. So now we've identified the electron poor and the electron rich. So that means that this is going to attack that. And when it does, it forms a bond with the hydrogen. And in the process, another bond is broken. This bond right here has to be broken. Those electrons are transferred to the oxygen. So that means we're breaking the bond here with the electrons staying with the oxygen. And this pair is forming the bond with hydrogen. That's called a coordinate covalent bond. You remember from general chemistry. A coordinate covalent bond is one in which the bond forms by donation of both electrons of the bond coming from one side. And what we end up with is ammonia and a methoxyl anion. That's the proton transfer. Okay. To simplify things, when we start actually getting into multi-step reactions where we're combining elementary steps, it's useful to simplify the situation because it can get complicated really fast and muddy the waters, so to speak. So these are some simplification tips. Anions, when you have them, do not exist without the presence of cations. Right? Now they can in the gaseous state, but we're largely not conducting those type of reactions. In the solid and liquid phase, if you have an anion, there's going to be a cation somewhere. But those cations, if we're talking about hydroxyl in this case, hydroxyl is our electron rich, our nucleophile. And we can approach it, the reaction, as if the cation, the sodium ion in this case, it isn't exist. It's not there. Well, it is there, but for our purposes, we don't have to consider it because it's a spectator. All right, so that's one simplification. Get rid of the spectator ions. Okay, so if we're doing a proton transfer between potassium methoxide, KOCH3, and hydrocyanic acid, then we look to see how can we simplify this thing. Well, we can view the potassium ion as a spectator. So we're really only dealing with the methoxyl anion. Right? So we have this methoxyl anion here, right, with our CH3 group here, and this has a negative charge, right? This is actual charge on that group, and oxygen has to have an octet, so it's got 3 lone pairs. All right, that's our nucleophile. The let's see. Now that doesn't make any sense because H2N minus, hold on a second. I think there's a mistake in this slide. We're looking at HCN, not H2N minus. Yeah, that should be HCN. HCN in this case this is, the hydrogen here is electron deficient. In other words, it's slightly positive. And the reason for that is twofold. This nitrogen is an electronegative atom, and it, by induction, is drawing electron density away. But we also know that the effective electronegativity of carbons increases with double and triple bonds. So this is even more electronegative here. So we're drawing electron density away from that hydrogen, making it positive. So that's the electrophile. This is the nucleophile. Now, see, there they have it correctly written. Okay, in this case, we've done away with the potassium. It's a spectator. So now we have this electron rich that's going to attack that hydrogen. And when it does, this bond breaks. Like that. So now what we have is CH3OH with this new bond. And we have this anion, like that. Okay. Now, 246. They didn't draw in the lone pair on the nitrogen. There should be a lone pair right there on that nitrogen, because it has to have an octet. 2468. All right. When we're dealing with organometallic compounds, that is where the metal is bound to the carbon, directly to the carbon. The carbon metal bond acts as a polar covalent bond, so it's very, very polar. The metal wants to give up its electrons, like all metals do. They want to give up their electrons. So that makes the carbon electron rich. They can be treated. We can ignore the metal and treat the carbon part of the compound as an anion, a carbanion. Then it makes it easier to deal with the reactivity. I showed you the other day a Grignard reagent where we had magnesium and a halogen bound to a carbon. We know that exists, but when we try to create a mechanism for the reaction, we can ignore the magnesium and the chloride. Right. If we have a carbon here bound to something else, and then we have a magnesium and say a bromine, then we can ignore that part right there. And for our purposes, we can say like that. And that's how we treat it, as an electron rich or a nucleophile carbanion. All right. The Grignard is one possibility. There are also organolithium compounds. This compound where you have lithium and copper both bound to methyl groups. In that case, we can ignore the metals and actually treat the methyl groups as carbanions, each one of them. All right. If we have a hydride reagent, in other words, if you have a metal bound to hydrogen, we call that a hydride. Okay, be sure this is staying on screen there. So if I formed a let's see, our example here is a lithium aluminum hydride. So if I wrote aluminum hydride, it would be like this. It'd be a neutral compound. But if we add lithium to it, then we have the opportunity to add another hydrogen. And in that case, the whole group is negatively charged, and we can treat each one of those hydrogens as a separate hydride. In other words, with extra, it's got a duet, and that gives it a minus charge. We can do the same thing with sodium borohydride. Now, we know those compounds exist entirely, but for reaction purposes, we can treat them as just simply the hydride ion. And that really does simplify the whole situation. Okay, here's the next elementary step. Right, number 2. This is an SN2 reaction. Well, let me be consistent. the way they're writing it, they put the N down here and the 2 up here. Okay, what do those letters mean? S stands for substitution. N stands for nucleophilic. And 2 stands for bimolecular. So that means in this elementary step, you have 2 molecules that are reacting. And the mechanism says that one of them is a nucleophile doing the attacking. And when it does, it forms a bond. The nucleophile forms a bond, and it substitutes for a leaving group. Okay, so here's an example where we have a nucleophile. This hydroxyl is very effective nucleophile. And we have this methyl chloride molecule. And chlorine ion makes a very good leaving group. That is, it's very stable. It's a large atom, forms a large ion, and it stabilizes. When the larger the ion, the more stable the negative charge, because it can be, the charge can be distributed over a larger volume. So chlorine makes a very good leaving group. Bromine does, iodine does, make very good leaving groups. So what we're doing is we're attacking with this nucleophile, that substrate, and the carbon is electron deficient. The reason being, chlorine is electronegative. So it's drawing electron density away from the carbon and making it slightly positive. So this SN2 reaction substitutes the hydroxyl for the chlorine. And what we've produced as a consequence of this reaction is methanol with chloride ions as the leaving group. The second example that's given there is ammonia is attacking this other molecule that'd be difficult for me to name right now. But you'll notice that the leaving group is the one that is bound to the carbon by way of one of its oxygens. So the carbon itself now, in this case, is deficient. It's slightly positive. So that ammonia attacks that carbon, and then the leaving group is this methyl sulfonate, I think we call it, methyl sulfonate ion. And it's very stable as a leaving group because it's huge and because it can resonate, right? If we resonate that one, let's see, we have sulfur here, we have oxygen, oxygen, oxygen with a negative charge. Let's see, there, and there two, there two there, two there, and we have this methyl. Okay, how can that resonate? Well, it can resonate by shifting that negative over here, right? Making that double bond. Or it could do the same thing on the other side. It has 3 possible structures, and that resonance stabilizes it. In addition to this large size for the negative charge, the resonance stabilizes that leaving group. That makes it a good leaving group. Okay. If we look at the free energy diagram for this nucleophilic, this SN2 reaction, where the nucleophile attacks in this case, the R group, and then the leaving group leaves. Let's see, lost my train of thought. Okay, what we're showing here is that with a little bit of rise of energy, we get a transition state, right? Where we're starting to form the bond between the nucleophile and the R group, and we're starting to break the bond between the R and the leaving group. That's the transition state. Then if we have just enough energy to go over that hump, now we end up with products that are lower in energy. Okay. All right. I mentioned characteristics of the substrate, actually the leaving group. Substrate is the molecule that actually contains the leaving group. Okay. The leaving groups have to be relatively stable once they have left. That's the whole idea behind a good leaving group. It's more stable, separate from the molecule than before. Now, these leaving groups are very often conjugate bases of strong acids. Right? So think of a strong acid. Like hydrochloric acid, right? What would its conjugate base be? Its conjugate base would be that. Okay? That's a good leaving group. Why? Because it doesn't want that hydrogen back. It's perfectly happy just like that. Or how about sulfuric acid? Right? I forgot the hydrogen here. Okay. Hydrogen. And then what's left over? HSO4 minus. If that were attached to a molecule, it would be a good leaving group also. The nucleophile, and this is a restatement actually, a nucleophile tends to be let's see. Yeah, a nucleophile tends to be attracted by and form a bond to an atom that bears a partial or full positive charge. That just goes without saying. I mean, it's that electron deficiency that draws the nucleophile in. Let's see. Common leaving groups. Let's mention those. Right. I mentioned them already. The halogens, right? Chloride. Fluoride is not there. It's not stable as an anion. So fluoride would not be a good leaving group. But chloride is, bromide is, iodide is. Those are all good leaving groups. And the reason fluoride is not is because hydrogen fluoride is a weak acid. Right? So the conjugate base, the fluoride ion, is not the conjugate base of a strong acid. It's the conjugate base of a weak acid. Other common leaving groups are anions that have substantial resonance stabilization. I just showed you one. There's another one. This group right here is also very stable. Water and alcohols are common leaving groups because they're conjugate bases of strong acids. Like, if water or an alcohol is the product of leaving, then it is the conjugate base of a strong acid. H3O plus is the strong acid, so the leaving group would be water. Okay. And this type of alcohol is a strong acid because it prefers to be like this. Right? So a conjugate base of strong acids means that these make good leaving groups also. They're neutral leaving groups, whereas these are charged leaving groups. All right. What are good characteristics of a nucleophile? Remember, nucleophiles are electron rich. They will either have a full negative charge or a partial negative charge, right? So they don't have to show the negative charge. They could be only partial. And they will have lone pair electrons. So whether they have a positive charge or not, they will have the lone pair. And some common negatively charged nucleophiles, the strongest one of all is the hydroxyl. But these other charged species also have lone pairs available. They're good nucleophiles. Uncharged nucleophiles are like ammonia. Ammonia has a lone pair, right? This methylamine has a lone pair. Water has two lone pairs, right, on the oxygen. This oxygen has two lone pairs. That sulfur has two lone pairs. And that sulfur has one lone pair. Wait a minute. No, it has two lone pairs, right? Yeah, two lone pairs. So the lone pairs are always there. Charge may or may not be there. The full charge, but a partial charge could be there. All right. So let's ask this question. Can methane act as a nucleophile in an SN2 step? All right. So what does methane look like? Right? Does it have a partial charge or a full negative charge? No, it doesn't. Does it have lone pairs available? No, it doesn't have those either. Right? So what we're saying is that methane would not make a good nucleophile. It has neither a partial charge, nor does it have a lone pair. So methane, don't ever try to make methane a nucleophile. That's the lesson here. All right. So I think the point of this slide is we're trying to draw a comparison between what we know so far, the proton transfer and the SN2 reactions. How are they similar? How are they different? Obviously, the proton transfer removes a proton from an electrophile and transfers it to the nucleophile. But the SN2 reaction, there's a leaving group, right? I guess you could consider chloride a leaving group in this case. But it's definitely a leaving group in the SN2 type reaction. Nucleophile, the same nucleophile in both of these examples, instead of attacking the hydrogen in the SN2, it attacks the carbon. The carbon is the electron deficient species. And then chloride, again, is the leaving group. So there are your similarities. And in the process, you still have the hydroxyl added to either the hydrogen or the methane. All right. Let's see can we draw the SN2 step that would occur between this species. Now, C6H5 is going to be that benzyl, the phenyl form. And then we're going to attach let's see, where do we want to attach? CH2. And then we're going to attach an iodine to that one. Okay. Then we want to react with that CH3, C, no, S, excuse me, S. And notice we have this metal, this sodium metal. That sodium metal is a spectator. So we're actually saying this is negatively charged, and it has 3 lone pairs. Okay. So we have to identify, where's the nucleophile? There's the nucleophile, excess electrons. Where is the electrophile? The electrophile is deficient. In other words, this ion is drawing electron density away. So this is slightly negative, this is slightly positive. And this also, this benzyl ring also contributes to the fact that this carbon is slightly positive charge. So we've got this here, this lone pair is going to attack that carbon right there. Okay? And when it does, that pair of electrons added here, it's already got 2, 4, 6, 8. It's already got an octet. So if we attack it with 2 more electrons, it's excess, and we can't allow that. So in order to compensate, this bond breaks and delivers those 2 electrons to that iodine. Okay, that way, what do we get? Well, we get, I have to draw it smaller. What we get is this carbon bound to this sulfur, bound to that methyl group. And now we only have 2 lone pairs here. And plus, we have this free negative iodine. Okay? Okay. It's going to take practice. That's all I can say. The more you do these, the more comfortable you'll feel. And we're starting off with the elementary steps so that we're not complicating things too much in the beginning. These are typical elementary steps that you will encounter in future multi-step reactions. Now, for this course, CHEM211, we're going to introduce some multi-step reactions by combining some of these elementary steps. That'll occur in Chapter 8. But then in 212, we're going to go from the sublime to the ridiculous. We're going to go all out on multi-step reactions. And we're going to look at competition. This is just a preface. All right. 2 of you are not going to be in that in that mess. 1 of you is. So when we get to that point, we're going to take all these elementary steps, the most common ones and the most likely ones, and try to decide which one is the predominant one. All right, so that's where we're headed with that. But right now, we're just elementary steps. So we've covered proton transfer, SN2, nucleophilic substitution, bimolecular. Okay. Come on. Are you happy now? I got a cat that wanted in the room. You want to come up here and say hello? Hmm? Come on. Here. Come up here. Come up here and say hello. Here we go. Right. Say hello. No. Why don't you get over here on the side? There you go. Lay down, take a nap, or look out the window. Okay. Within these elementary steps, we can talk about the formation of a bond or the breaking of a bond. And typically what we see is the type of bonds that are formed are coordination bonds. In other words, the electron pairs are donated by one of the reactants. Remember, that's coordination bonding. We covered that in general chemistry. So in this example, this coordination step, where we have this nucleophile, this bromine anion is the nucleophile, and this carbocation is electron deficient. Notice it's only got 6 electrons, right? So it doesn't have its octet. It needs 2 electrons to make an octet. So it gets them from bromine. And I would also emphasize that the bromine is a Lewis base. Remember, all right. For those of you that have had general chemistry, second semester general chemistry, you were introduced to the concept of a Lewis base and a Lewis acid. One of you hasn't got there yet. That's in our chapter 14 and 15. But when a Lewis base, for now, just accept this as gospel. A Lewis base is an electron pair donor. That's a nucleophile. And a Lewis acid is an electron pair acceptor. That's an electrophile. And what we get is a carbon with an octet, and the bromine still has its octet. And we've formed a bond between the carbon and the bromine. Here's another example where we have this carbonyl, this, let's see. Oh, methyl carbonyl chloride. That'll do for now. But the Lewis base is the chloride. And the chloride attacks the aluminum that's bound to 3 chlorines. The aluminum is going to be electron deficient because it's a metal, right? And it's bound to chlorines, which are drawing electrons away from the aluminum. So the bond that forms makes chlorine a formal charge of positive and aluminum a formal charge of negative. Right? So in this case, we have the product is charged. Well, actually, it's balanced charge, but parts of it are charged. That's a coordination step. Usually, coordination steps produce unstable products. Now, the flip side of that coin is the heterolytic bond association. That is, we're going to break a bond, and in this case, excuse me. When we say hetero, we mean other. So you can think of your molecule as having 2 parts. You have the one and the other. And the other is going to get both electrons. The leaving group gets the electrons. So in this case, we have cyclohexyl iodide. and the bond breaks here and donates those 2 electrons to the iodine. So now we have an iodide ion, and we have a carbocation, a cyclocarbocation. It's you can think of the heterolysis as the reverse of coordination. In other words, we could go backwards, right? Go back to the previous slide and say, okay, now this was the electrophile, and it's going to attack that deficient carbon. Right? So it could go either way. Here's another possibility. Actually, that one looks familiar. Yeah. This is the one we made on the previous slide. So now, what can we do? Well, we can take those electrons from this bond. Remember, the curved arrow always starts with a lone pair or a bond. And we show the electron movement. The electron movement here is going from the bond to the chloride, to the chlorine, and it leaves us with a carbocation here. Let's see. That leaves us with a different product, though. Right? We formed the this species here, but now when we look at it here, it wants to do something else. So instead of going back the way it was, this bond is the weaker one. Right? So those electrons are going to travel here, and we produce 2 different species from the heterolysis of that compound. Now these, the coordination steps or the heterolysis steps usually are part of a multi-step mechanism. Right? You never see them by themselves. All right. Now we come to another possibility, nucleophile elimination. Let's see. Does it have a, I thought it had a, okay. I might have to erase this to keep giving us room here. All right, so this one's going to be a nucleophile, right? Nucleophilic elimination. Ah. Elimination. All right. So these are nucleophilic addition steps, the SN2s, right? We've got bimolecular, and we have a nucleophile attacking an electrophile and adding itself to the molecule. So we only have one product. The nucleophilic, that was the nucleophilic addition steps. There's several examples. Let's see. And this is the generic for the nucleophilic addition. All right. So then, there was no elimination in here, was there? No, there's no elimination there. Elimination's on this slide. The nucleophile elimination, hold on a second. You know, I think this is still part. Okay. Okay. This is a special case of nucleophilic addition where we have one of the atoms, the carbon, is attached to by way of a pi bond, one or more pi bonds. And these pi bonds are polar. That makes the carbon electron deficient. So when it does that, we're actually unstable. Yeah, we're actually unstable. What has happened is the two of the electrons from the pi bond are transferred to the more electronegative atom. The reason for that is you cannot exceed the octet on a carbon, right? So if we left it there, if we formed this bond and we left that double bond there, then carbon would exceed the octet. So in order to compensate, we break that one of the pi bond and put those two electrons in this oxygen, which makes it negative. Okay, so now that it's negative, let's see. I'm looking for an example. Here we go. So for this one right here, on the next slide, now we have that chloride attached. What it does is the chloride is the leaving group. This is the elimination step. So we have the nucleophilic elimination occurs after the addition. So we add and then we eliminate. So actually those are two steps. So let's see, where did we start? Right here, we started here with chloride, a methyl group, and oxygen, well, a carbonyl group. Okay, then when we eliminated the chloride, what did we have left? Well, when we eliminated the chloride, now we have two methyl groups on that carbon, where we only had one before. Wait a minute. No, that's not the right example. I'm sorry, that's not the right example. This one resulted from a different attack. But in the event that we did form this oxygen, negatively charged oxygen, now in order to stabilize the molecule, we got to get rid of something. So we get rid of the chloride and we reform the double bond. See, there's our good leaving group. We could do the same thing here with the nucleophile elimination, where we have an amine group attached to the carbon, and we have this looks like a water, right? So we have to eliminate. Water is a good leaving group, right? We said that earlier, and that will stabilize the situation. Now we come to a bimolecular elimination. This was a nucleophilic addition followed by elimination. Addition, and maybe that's 3 and 4. Elimination. Okay. Now we have 5, which is going to be an E2. This is a bimolecular elimination step. Okay. So we have 2 molecules that are reacting, and we're going to eliminate something. We're not just adding. Nucleophilic substitution. The nucleophilic substitution, let's go back. All right, let's go back and just reminisce for a moment. Okay, here's the substitution. Notice that this nucleophile is attacking that carbon, and it's substituting for the chlorine that was attached to that carbon. So we're substituting this OH for that chlorine because they both are temporarily attached to the carbon. Right? Let's see. Where's that diagram? Hold on a second. Let me go back. I want to find that intermediate. There it is, right? So in the SN2, this nucleophile is attacking that, usually a carbon. And then the leaving group is leaving that carbon. So that's the substitution part. We're substituting this nucleophile for that leaving group. Okay, now let's go back to the E2. E2, there we go. In the E2, the bimolecular elimination, we are attacking some species, in this case hydrogen, and that frees up these electrons to form a double bond, a pi bond there on those, between those two carbons. And then the leaving group is not leaving from the original carbon, it's leaving from the second carbon. Okay? All right. So that's why we call it elimination rather than substitution. We're eliminating the leaving group from the second carbon, the neighboring carbon. And that's typical. Also, what you will notice is that whenever this happens, we form another pi bond. Sometimes we form a double bond, and if the double bond's already there, we'll form a triple bond. That's characteristic of the E2. We got to form that carbon-carbon pi bond. Okay, here's some other examples. So notice that this is probably going to be the leaving group right here. This is the nucleophile, and this hydrogen is deficient. Right? It's the source of the attack. It's the electrophile. And when it does attack that hydrogen, it removes that hydrogen, and the heterolysis produces two free electrons that go into a double bond between these two carbons. Now, the carbon that's identified with the attacking source is the alpha carbon. And the carbon that's identified with the leaving group is the beta carbon. So for that reason, it's called beta elimination. The elimination, the leaving group leaves from the beta carbon. And we formed a double bond. All right, here's another example. Let's see. Here we have this amine anion is attacking that hydrogen. It could have attacked this hydrogen or the other hydrogen. It doesn't matter. Right now, it doesn't matter. Let's put it that way. And there's our leaving group, right? So we've already got one pi bond. We're going to form a second pi bond. So what we end up with is ammonia and acetylene with bromine as the bromide ion as the leaving group. All right. That's the E2 format. So still, this is still consistent with all of our reactions. Electron rich attacks electron poor. So in these E2 steps, here in this case, we have a Lewis base attacking the substrate, right? So now you may wonder, why doesn't it attack that carbon? Well, if it attacks that carbon, then we have an SN2 reaction. We don't have an E2 reaction, right? So, and we also will not get a double bond. So if we look at the outcome of the reaction, if we see a double bond where there was a single bond, then it's more likely that we have an elimination reaction rather than a substitution reaction, because substitutions don't produce double bonds, right? Elimination reactions do produce double bonds. That's why when we see that as the outcome, or if we predict a double bond formation as the outcome, then it has to be E2 versus SN2. I'm trying to anticipate your questions since there's nobody here but me. All right. Other possibilities. So if we have an electrophile, let's see, electrophilic addition step, right? We have a nucleophile attacking electrophile, and the electrophile is added to the carbon, right? So this is an electrophilic addition step. This is number 6. Electrophilic addition. And we're probably going to have, we're going to have an elimination too. So we've got 6 and 7 here, right? Those two together, these two together. What happens with electrophilic addition is the pi electrons in a double or a triple bond attack an electrophile of some kind. And when they do that, they form a bond between one of the carbons and the electrophile. And when that happens, this coordination bond that forms, right, with those two electrons, both of them are used to bond to that electrophile, which means that now this carbon is deficient. We have taken one of its electrons away. So now it's missing an electron, and it's a positive charge. That's a carbocation. It's also, let's see, hybridization would be an sp2 hybridization. And that's unstable in this case because it's deficient, right? It has an SN2 will be like this, that, and then it has unused p orbitals, right? That's where the positive charge resides, in those unused p orbitals. That's an understatement. These carbocations are very unstable, and they will always react with something else to reestablish their octet. Right? So very often what happens is if you want a very reactive species for a subsequent reaction, you use an electrophilic addition to produce the carbocation, and then it can react with something else immediately. All right. Another thing that we notice is that nonpolar pi bonds, like this one, act as nucleophiles in this case, in this electrophilic addition step. And unlike other nucleophiles, there's no atom with a lone pair that also bears a full or partial negative charge. Those pi electrons are not associated with lone pairs. They're not associated with a partial negative charge. Right? This is a perfectly nonpolar bond. That's one distinctive feature of the nucleophile in this case and the nucleophile that we've seen so far. Okay, here we've got, let's see, what would this be? That'd be 1, 2, 3, 4. carbons, which is butane. So it would be but-2-ine. But-2-ine. That's the name of it. Okay, this is our nucleophile. It has these pi electrons, and the electrophile is this hydrochloric acid. Right, so the hydrogen is electron deficient. We form a bond between the carbon and that hydrogen and free the leaving group, chloride ion. Right, so now we have a carbocation with also a double bond. Here's another electrophilic addition. Right, we have a NO2 cation that serves as the electrophile, and then this benzene ring uses one of its. This is a little misleading, but it's useful the way it's presented, because we know that there are no double and single bonds in this ring. Right. This is a benzene ring. Right. So those electrons are distributed throughout. So what happens is somewhere in that molecule, 2 electrons attack that NO2 plus. And wherever it wants to, we don't know, the bond forms between one of the carbons and that NO2. And then the adjacent carbon becomes the cation. And at that point, we don't have a benzene ring anymore. And it's very unstable, to put it mildly. All right. Now, how about electrophilic elimination? So once we form the carbocation, we can eliminate. Right. Now this one, it appears to be essentially the reverse of the previous ones. Right. We've got this electrophile that was added, right, by let's see, let's go back. Yeah, forms the carbocation. I want to go further. Here we go. This is the more useful one. So we've got this alpha carbon has the electrophile on it. The beta carbon has the carbocation. All right, so let's go back over here. Now we've got this one again. Right, there it is. So what happens is, in order to reestablish the octet for that carbon, this sigma bond breaks, and those 2 electrons are donated over here to form the double bond. And we eliminate the electrophile as a positive ion. This one is uncharged and very stable. This one is still electron poor. So I could conceive of a situation where you would have an equilibrium established between those 2 reactions, the electrophilic addition and electrophilic elimination. Not always the case, but in this particular case, we could make an argument for that. So here's another one, right? We have this carbocation here. We have a leaving group there that breaks the bond, forms a pi bond to complete the octet for the carbon. And because we add 2 electrons here, then we neutralize that positive charge. Now we have this nitrate group, nitro group still attached, and the leaving group is gone. So now we have nitrobenzene. Now in this case, we have water attacking that hydrogen, forming a double bond. Right. In this case, actually, electrophilic elimination, this is bimolecular. Right. This is unimolecular up here. This is bimolecular. right? So this Lewis base attacks that hydrogen, and the electrons that are given off stabilize that, eliminate the carbocation, actually, form the double bond, methylpropene, and now we have this strong acid, the hydronium ion. The reason, okay, here's the reason that we have this water attacking. The water is in the solution, right? It's always there. The reason we have to do it this way is because hydrogen ions never exist independently. They have to be attached to something, right? So we don't really consider this a biomolecular process, right? That hydrogen when it leaves, it has to go somewhere. So it goes to the water molecule. That's why it's still considered electrophilic elimination. And it's unimolecular. All right, let's talk about carbocations a little more. So what can a carbocation do before it reacts? Well, one of the ways that the carbocation can behave is if there's a hydrogen on the neighboring carbon, it can shift over and take the place of that position on the carbon atom, and then the carbocation then shifts to the other carbon. So it can flip-flap back and forth. That's known as a 1,2 hydride shift, right? The hydride, or the hydrogen, shifts between the 1 and the 2. Okay? That's fairly simple to understand. Now the shift, this is a process called rearrangement. Now, how it happens, we haven't talked about it yet, right? Does it directly go over there like that? Right? And the hydrogen shifts over there? Probably not. It goes through an intermediate step, I think. Or if you don't have a hydrogen there, but you have a methyl group, then the methyl group can shift. It can be rearranged. We can rearrange by moving the methyl group over there. And the carbocation now resides on the other carbon. All right. Oh, excuse me. Up to this point, we've simply addressed these elementary steps in terms of a mechanistic approach. Now, as we're saying, they occur, so how do they occur? And using curved arrows, we account for the bonds breaking and the bonds forming. But we often are faced with the problem of, why does it occur in the first place? I mean, what's the driving force? Well, the driving force for a reaction is a reflection of whether products are favored or reactants are favored. The driving force can drive toward products as written, or it can favor reactants. And this is often associated with the introduction of the concept of Gibbs free energy. A lower Gibbs free energy indicates greater stability. So if we draw that on a diagram of some kind, right, the energy here, then we would say that this side is more stable than the other side because there's a lower free energy. We also look at this in terms of a change in free energy. Remember our previous discussion about the delta G and whether a reaction is spontaneous or not. If delta G is negative, then thermodynamics tells us, the second law of thermodynamics tells us that the reaction is favored in the forward direction. It's spontaneous. We also notice that depending on the stability of the products, which is related to the free energy, the more stable the products, the more driving force there is to produce them. So increasing stability in the products increases the driving force toward products. So we can look at that in terms of charge stability relative to the reactants. If there is any charge available, whether it's a full charge or a formal or a partial charge, right? Where is it more stable? Is it more stable on the products or on the reactants? If it's more stable on the products, then the reaction is driven toward products. And we can also look at it in terms of not just bond energy, but, not just charge stabilization, but in terms of bond energy. Right? So the greater bond energy in the products would favor products over reactants. And that's a confusing point sometimes when we talk about bond energy. The way bond energies are described, you have something here, like that, and then you have this one separate from that one. The bond energy is how much energy does it take to break that bond. So it takes more energy to break this bond, to get those, for some than others. And if it takes more energy to break the bond, it's said that the bond is higher energy. When in fact, I don't think that's right. Total bond energy favors products. Okay, if we went the other direction, if we went this way, what would happen? We would give up energy, right? That would be an exothermic process for these two atoms to come together and form that compound. That would be a more stable situation. Okay. So we're looking at two competing effects: stabilizing the charge and what's the total energy of the products relative to the reactants. So if we're looking at charge stabilization, in the case where charge stability is favored over bond energy, we look at, in this case, we're reacting NH2 minus with hydrochloric acid with a proton transfer. Now look at the negative charges. On the left-hand side, we have a negative charge, which is on the NH2. Whereas on the right-hand side, we have negative charge, which is attached to the chloride ion. So which is more stable? Actually, the chloride ion accommodates the negative charge better than the nitrogen. And that's largely due to a higher electronegativity for chlorine. But if we looked at bond energy and we looked at actual values, the bond that is broken versus the bond that is formed. So the nitrogen-hydrogen bond is the bond that's formed. The chloride-hydrogen bond is the one that's broken. Okay? So it takes more energy to break the hydrogen chloride bond. So that's the more stable bond. But in fact, if we look at the equilibrium constant for this reaction, we find that 10 to the 43rd says the forward reaction is massively favored. So that means that charge stability wins out over bond energy. And where you have two of them juxtaposed, where you're trying to decide, is it bond energy or is it charge stability that's winning? If you have no other information, go for charge stability. Charge stability will usually win. Let's see. Yeah, here's another case where charge stability is favored over bond energy. In this case, we have the charge is on the hydroxyl. And then in the products, the charge is on the chloride, and the chloride is more stable than the hydroxyl, simply because chlorine is more electronegative than oxygen. Excuse me. Plus, chloride ion is much, much larger than the hydroxyl. Much larger. So you get the electron density spread over a larger volume. That makes it more stable. How about the stability? How about the bond energies? Right? What's the difference in bond energies? What we see is that the carbon-hydrogen bond is broken right here, right? And it forms a double bond. And the carbon-chloride bond is broken. And the bonds that form are the ones between the oxygen and the hydrogen and the added bond between the carbon and the carbon. In this case, the sigma bonds are the total bonds broken here are exceed the amount of energy that's gained by forming these bonds over here. So there again, we're saying bond energy favors the reactants, whereas charge stability favors the products. And in this case, we're still the products are favored. Right, there it is again. You have a battle between bond energy and charge stability. Charge stability wins. Now, what about charge stability in carbocations? If your reaction forms a carbocation, under what conditions would the carbocation be most stable? Right? Well, this example here, the allyl carbon cation can resonate, right? So that helps stabilize it. This oxocarbenium ion here, where it has an oxygen bound to two carbons, and one of them is a cation, this ability to resonate also stabilizes. This benzene, which has a carbocation starts on the primary carbon, can be stabilized, resonantly stabilized, by moving the carbocation onto the ring. Once it moves onto the ring, that carbocation can move over here, and here, 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 or even here, actually. So you have lots of stabilization there. this would be probably the most stable of these three because of the resonance stabilization. Now, when we're comparing methyl groups as carbocations versus primary carbons versus secondary carbons versus tertiary carbons, we find that the more carbons that are attached to the carbocation, the more stable it is. This alkyl substitution stabilizes the carbocation. Now, there's the process that occurs is called hyperconjugation. There's another slide coming up that we'll try to explain what that means. But it's responsible for the stabilization of the tertiary carbon is the most stable of this group. Now you can get other types of carbocations introduced. The allyl is about as stable as the secondary carbon, and the tertiary carbon is about as stable as the oxycarbenium ion, which is about as stable as the benzyl. So those are the trends. Okay. So let's see if we can say which one of these would be the most stable carbocation. All we have to do is, in this case, look at the connectivity of the carbon. Right? This carbocation is attached to how many carbons? 1, 2, 3. I don't know why they drew that red arrow in there. Which side of this carbon? Oh, excuse me. We're doing a hydride shift. Not a hydride, a methyl shift. Right? This is a methyl group. We're going to shift it over here onto that carbon. Right? And that moves the positive charge over on this carbon. Okay? So we have a methyl shift here. This methyl shift, which way is favored? Right? Would this be more stable or would that be more stable? Actually, this one is more stable. Right? This is a tertiary carbon, which is more stable than a secondary carbon. And that's what all this discussion says. It says just that. Now, on the next slide, we're going to look at the hyperconjugation argument. It's a little difficult to understand because it incorporates molecular orbitals, but let's try to make sense of it. Okay, so if we start off with this methyl carbocation here, right? There's no way for it to interact with any other carbon atoms, right? There are none around, and hydrogen's not going to be any help. But if we add a carbon over here where that hydrogen is, right? Now we have this filled carbon-hydrogen sigma bond here, this molecular orbital, which is represented here. And we have this unfilled p orbital here, which interacts with this molecular orbital and tends to stabilize it. It reduces, see, its energy is up here, right? The energy of that unfilled orbital is up here. The energy of the sigma bond here. And when we combine the two, we get another molecular orbital that's lower in energy. So that's, the term for that is hyperconjugation. It's stabilization of a carbocation by the sigma bond attached to a neighboring carbon. All right. Here's something else that can happen. This is called tautomerization. And in this case, which can be a number of different types of equilibrium between isomers, right? These two are isomers of one another, right? They're attached, carbon, carbon, oxygen, carbon, 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 oxygen, right? But they're bonded differently. Right? So their form is said to be tautomerized. This is the keto form, right? Where you have a carbon, 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 and then the middle carbon has a carbonyl. Right? If, on the other hand, you have the shifting from the beta carbon to the bond between the alpha and the beta carbon, right? These electrons shift over here. That leaves, and you move a hydrogen at the same time, then you get an alkene and an alcohol. So this is the keto form. This is the enol form. Ene from alkene, ol from alcohol. Keto, enol form. And this can occur under either basic conditions or acidic conditions. All right, let's look at the mechanism that accounts for this. Let's see. I probably should add that here, shouldn't I? 8. Keto enol tautomerization. There we go. All right, so here's the keto form. And in basic solution, this is the proposed mechanism, right? This actually, it's a two-step process. So this technically is not an elementary step. This is a complicated step. This is the proposed mechanism. Let's just go at it. That hydrogen is supposed to be slightly deficient. So if we transfer that proton to this hydroxyl and make water, then where do those electrons go? Those electrons go to this carbon. Right? That gives it more, let's see, no, it has its octet, right? 2, 4, 6, 8, but now it's charged. So what we do is those two electrons go over here to form a double bond. All right, when they do that, when they form that double bond, now that carbon exceeds the octet. So we're going to break a pi bond here and put those two electrons on that oxygen, and that makes it negative. Okay, so when it gets that negative charge up there, the we do a proton transfer. The proton transfer now comes from this water molecule that we formed first, and that proton now is attached to that oxygen. That makes the alcohol group, and now we have the ene, the alkene now. Okay, that's under basic conditions. Under acidic conditions, we follow a different path. Under acidic conditions, where you have excess hydroniums, now the oxygen attacks that hydrogen, and we've got water left over. And now we have this positively charged oxygen. All right. So what we do now is we transfer those electrons to that oxygen. That makes this carbon deficient. Then this water does a proton transfer for that hydrogen, and those electrons are transferred to this bond and makes that double bond. And now we're back to the acidic conditions. So under basic or acidic conditions, the degree of acidity or the degree of basicity doesn't change. They only act as, I hesitate to say catalyst, but they do facilitate the reaction. They participate in the reaction, but they're not used up. So technically, that's a catalyst. And you end up with the same thing, an enol, where you started with a keto. All right. Now the question becomes, is one side favored over the other? Let's see. I thought we already looked at that one. Oh, this is going backwards, right? We went from keto to enol first. Then this goes from enol to keto. Right? It should just be the reverse. Yep. Yeah, it's just the reverse, right? Right. So you just reverse the reactions, right? Go from one direction one way, you go the other direction the other way. All right. Now, here's the rest of the story. When you're comparing the amount of keto form to enol form, we find that the keto form is more stable. And that favors, and these are measurements that have been made. So these measurements show us that the keto is more stable in all these different types of tautomerization. The enol is less stable. And also you'll notice that the keto and the enol forms are not charged. So that means we can't look at charge stability as the reason. We have to look at bond energies to shine light on why one side is favored over the other. So that's what the next slide is going to do. Right? So if we look at each of these bonds in the enol form, and we add them up, the total bond energy here in the enol form is 1,430 kilojoules. The total bond energy for the keto form of those bonds that were broken and these bonds that were formed is 1,477 kilojoules. So the keto form is favored by 47 kilojoules, right, which is significant. And that's how we account for the preference for the keto form versus the enol form. All right, got one more slide. And this just emphasizes the fact that tautomerization occurs everywhere in your body. And the example here is part of the process of the way your body breaks down sugar, right? Simple sugar, glucose. First, it phosphorylates it, and then the phosphorylation leads to a tautomerization. And the tautomerization ends up with fructose 6 phosphate. So we go from glucose 6 phosphate to fructose 6 phosphate. We have the same number of carbons, but it's a different structure, right? And we go through that tautomerization process twice, actually, to get to this product. So glucose enters your cells, and they're phosphorylated, And then we go through 2 tautomerization steps to get to fructose 6-phosphate. And then we proceed from there to break the molecule down and extract energy from it. But this first step requires tautomerization, and it also requires enzymes. Phosphohexose isomerase does all of them, right? It does both of these steps. Right? That just illustrates the point that we're not just learning this stuff because it's, we're not learning this stuff just because you have to pass a test. I mean, this is important reactivity in every cell in your body. Okay, that's it. I've taken too much time as it is. So let me stop the share, stop the share, stop the share. There we go. All right. I must have missed a couple somewhere. There's supposed to be 10 elementary steps in there. So I missed them somehow. Maybe your textbook will be more descriptive. All right, so let me see. That takes care of chapter 7, the arrow pushing Wednesday. Okay, so we're going to have an exam on all this material on this coming Wednesday. And I also have a bit of news that just came through email. Let me check my emails and be sure it hadn't been updated. Okay, I did get a message from the dean, doesn't it? Okay, so here's what we're going to do. The 19th, the 19th of June is going to be celebrated in West Virginia as Juneteenth, celebration of the end of slavery. So that's going to be a holiday, and all campuses are closed on that day. That day is the day that we have exam 4. So that means we've got one more, let's see, 2 more classes. The next class we're going to have exam 3, and then we're going to go through interchapter C and D. And then the following Monday, we're going to get chapter 8. And then that following Wednesday, we won't meet. So what I'm going to do is I'm going to take that exam and put it in Brightspace. If I can get it into a form where you can take the test in Brightspace and it will grade it for me, that would be better. But if I can't, then I'll take the exam in PDF format and I'll put it in Brightspace so that you can print the exam and fill it out and then photograph it and send it back to me, or you can fill it out in your Acrobat Reader and answer all the questions and then just take the saved document and submit that. We'll talk about it again Wednesday. It's a mess, but like the dean said, she doesn't have control over the holidays. So when the governor says we're celebrating on June 19th and all state offices are closed, they're closed. So in my opinion, that's cheating you guys out of another day. But I can't control that. So this is my solution. We're going to have the exam in Brightspace. And I got to figure out how to best to do that between now and the 19th. So that's the end of this lecture.